Hello, everyone. Welcome to our live session. Today is Wednesday, May 11th. We're excited to have you all here, and there's been some exciting news, and there's going to be some exciting astronomy news this week. We'll get to that and more. Chris, why don't you go ahead and say hello to everyone, and we'll get started with questions.
Okay, welcome everyone to a live session associated with our online classes. Whether you're taking one of them or just found this by another means, welcome, and we're ready to take questions on astronomy, any topic.
All right, the first question today is from an email. Wendy asks, in the last session you were talking about the upgrades at CERN. Why is it that protons are smashed together instead of other subatomic particles that might shed more light on the knowledge of our universe?
Well, the nature of particle accelerators does vary. So Fermilab has had a long history of electron acceleration, positron-electron acceleration, and using linear accelerator rather than magnetic fields to curve a charged particle. It really depends on the energy you can get in the rest frame of a collision. And so with protons, of course, being almost 2,000 times more massive than electrons, and then accelerating them to nearly the speed of light, you get an enormous amount of energy from a proton collision. And of course, when you use protons and antiprotons going in counter-rotating circles, intersecting at a net almost twice the velocity of light, you get a phenomenal amount of energy. So, proton accelerators, heavy particle accelerators tend to be preferred. But you can certainly use electrons or electron-positron collisions, and other accelerators do.
And then kind of a follow-up question to that is secondarily, how does the Higgs boson give particles like the proton mass when it's so short-lived and unstable itself?
Yeah, there's some understandable confusion when people talk about the Higgs, because to physicists, the Higgs is really a field. It's not fundamentally a particle. What's the distinction? Well, the best way really in terms of its mechanism to think of the Higgs is that the Higgs is an ambient field that pervades space, and if you want an analogy, it provides sort of a viscous force for the particles that move through it. And it's essentially that sort of quasi-viscosity that gives particles their mass. So for some particles, the Higgs field viscosity seems higher, and so they have more inertia, so they have a high mass. And for other particles, it has lower viscosity and a lower mass. So it's this ambient field mechanism which ascribes mass to particles. Now you can put sufficient energy into a situation where you actually liberate the Higgs mechanism, the Higgs field, as a particle. You can create it momentarily, but of course it's going to disappear very rapidly by various decay paths. So it takes an enormous amount of energy to spontaneously generate this particle that's responsible for this underlying field. So this distinction between the particle and the field is an important one, and it's probably better or more correct physically to think of the Higgs as a field rather than a particle.
All right, the next question is from Hamid, who's on with us live. If velocity is relative, then every single in the universe is basically at rest except for the photon. So how exactly does this work? How does relative motion work if everything in the universe is stationary according to itself except for photons?
So photons propagate through a vacuum at the speed of light, 300,000 kilometers per second, and that's measured in a local inertial rest frame, or in a local rest frame as defined by special relativity in Einstein 100 years ago. Now, in terms of relative motion, the velocity of light is an absolute quantity, so it does not depend on the relative motion of an object or a receiving object or a transmitting object. And all the strange effects of special relativity, the sort of dilation of time, the distortion of space, and the increase of mass are results of the constancy of the speed of light. So operationally and by relativity and experimentally, first in the Michelson-Morley experiment, the speed of light is a universal parameter that does not depend on any kind of relative motion. Now, it is possible, of course, within the universe to define relative motion. So the Earth moves around the Sun has an orbit around the Milky Way is part of the Virgo cluster, and so on. So these are motions of physical objects that it's possible to define, and if you eventually get to a large enough scale, you find an enormous amount of mass in the universe that is not moving with respect to the universe as a whole in any net aggregate way, and that defines the reference frame, which we call the microwave background radiation.
And then a follow-up sort of related question to that is, why is linear motion relative, but we never hear anything about rotation, for example, in any of the Lorentz transformations?
So linear motion is the simplest kind of motion because with no external force acting, linear motion will continue. That's actually going back all the way to Newton's laws of motion. Nonlinear motion involves acceleration. So curved motion is acceleration. Constant velocity changing over time is acceleration. So curved or nonlinear motion is accelerated motion, and that's governed by different laws of motion because, of course, a force is involved. And so the real simple distinction is between curved or nonlinear motion or nonlinear direct motion and linear and constant motion. And the difference is that a force is involved.
The next question is from an email. Jan writes, is it possible for the stars in a very dense central region of a galaxy to spontaneously collapse to form a supermassive, or to form its supermassive black hole?
Yes, it's an interesting question, and people have wondered about this, and now, of course, they can do computer simulations to simulate it. It is indeed possible that if a sufficient number of stars are gathered in a deep gravitational potential well, such as at the center of the galaxy, you can have a sort of nonlinear collapse process whereby the stars will rapidly head towards the central mass concentration, the center of the gravitational potential. And that nonlinear collapse can indeed trigger the formation of a black hole. And it's possible that this is how the first black holes in the universe, in the smallest galaxies early in the universe, the ones that James Webb Space Telescope is designed to detect and discover, it's how those black holes formed. Now, something has to happen for that to be the case. Normally, in a stable dynamical situation, stars in a potential well will continue about their orbits. There will be some decay of those orbits over time, a natural process, but it's not going to be a rapid gravitational collapse as I described. But that mechanism does exist, and we think that it's operated in some cases in galaxies, in some cases even in globular clusters.
The next question is from Kendra, who's on with us live, and asks, could you briefly describe the Mayankovitch cycles, and does modern human influence on climate make the cycles less predictable?
The Mayankovitch cycles are named after a Serbian geophysicist from last century. I can't remember exactly what his time frame was. And he was using, geological record and astronomical information to infer cycles that are roughly 15, 30, and 100,000 year cycles. And these are associated with changes in the Earth-Sun orbital situation. So changes in the obliquity of the Earth, which is the tilt relative to the Sun, changes in the eccentricity of the Earth in its orbit of the Sun, and of course corresponding changes in the orbital speed of the Earth as it moves around the Sun. And there's a secondary influence of the Moon too. So these are very long time-scale motions, and they are repeating, periodic, and so people have looked for periodic signatures in the geological record. Now, it's really and notoriously difficult to tease out periodic long-time signatures in the geological record. So the evidence for the Mayankovitch cycles is significant, but it's not compelling, because the 100,000 year cycle in particular is particularly hard to pin down, because of course there are other enormous geological effects happening on these timescales that have nothing to do with the Earth's orbit. So these do seem to be real. They have a natural astronomical understanding, And I think their connection to climate change is significant over very long time scales, but it really has nothing to do with the situation we find ourselves in now, where the climate is changing due to human-caused creation of greenhouse gases in the atmosphere. These geological orbital effects are much more slow and subtle.
Maxwell Bennett is on with us live and would like to know, do you know, have there ever been surveys, or in your opinion, what percentage of professional astronomers accept the Big Bang as the correct model describing the early expansion of the universe?
I think there have been informal surveys at large cosmology meetings, including a couple I've been to. And the question is really not even posed anymore at a meeting, because essentially everyone is going to be on board. I would guess the number is probably going to be among professional astronomers, including people perhaps not working in cosmology, but just general astronomers, that 95% or more of astronomers would accept the Big Bang as the theory of how the universe originated, because the evidence for it is so strong. It is really one of the best theories we have in astrophysics.
The next question is from L. Ron Huss, who asks, is dark matter mere speculation, or do we have firm evidence for its existence?
We have firm evidence for the existence of a mass component of the universe that exceeds normal baryonic material. Baryonic material is protons, neutrons, and electrons, the stuff we're made of. We have evidence that this component of the universe exists and pervades the universe essentially on all scales, from galaxies up to clusters up to the universe itself, and exceeds normal matter by a factor of 6 or 7. And there's a good lot of evidence for this coming from many different routes. Probably the best evidence is from gravitational lensing, because mass bends light, and it doesn't matter whether the mass is visible or invisible, i.e. dark matter, it'll bend light according to general relativity. So our census of dark matter comes most robustly from gravitational lensing experiments, but that's corroborated by orbital dynamics of galaxies and clusters and stars and galaxies, and it's corroborated in various other ways. So there's a pretty compelling evidence for a dark component of the universe. However, that evidence doesn't tell us what that component is, and so we are still unsure.
The next question is from DS, who's on with us live. Is it true that objects on Earth have a greater effect on us gravitationally than the sun or moon? I remember Carl Sagan saying the midwife in the delivery room has a greater influence.
Yes, I think it's true, and Carl Sagan did say that. And I think the reason this is talked about sometimes is the idea of astrology. So the idea of astrology is that the planets and the sun and the moon have an influence on your behavior or your personality or the events in your life. And Sagan and others over the years have pointed out that given that the only way they could influence us in physics that we know is by gravity, the gravitational effect of any of the planets on you is indeed less than the gravitational influence of the person sitting next to you in the chair or the midwife when you were born in the hospital. So that's a fair statement. These objects exist, they have gravity, but its influence on an individual, a person on the Earth's surface, is dwarfed by other influences from nearby masses.
All right, so the next question, which will lead us into another discussion, Santosh sent an email asking, is it possible to send telescopes to outer space for gathering information?
We do send telescopes to outer space. The James Webb Space Telescope is a perfect example of that. It's just recently been sent 1 million miles from the Earth to a Lagrange point to gather information from the distant universe. And actually, more than a half dozen, perhaps 8 or 9 telescopes have been sent that type of distance from the Earth, to significant distance from the Earth. So we have telescopes in low Earth orbit, like the Hubble, and we have telescopes at much larger distances where the environment is very quiet and good for doing astronomy. So yes, it's routine to do this, and getting the data back is not difficult these days. What is difficult is being able to service these telescopes and fix them if something goes wrong when they're that far away, because astronauts cannot go there and do it.
All right, so that kind of leads us into some big news that has happened this week. The James Webb Space Telescope, or JWST, has posted a picture and announced that it is either finished or close to being finished aligning its instruments. Can you talk a little bit about what's next for the telescope and kind of what the time frame will be for James Webb's first real observations?
Right, so the James Webb has been through a series of successful hurdles since its launch around Christmas last year. It's the starting and extremely challenging hurdles it cleared were the opening up of the telescope, unfolding of these individual mirrors into a fixed structure, and the unfolding of the solar array, without which it would not have power to operate. There were many hundreds of moving parts involved in these mechanisms, and they all worked flawlessly. The next success, taking a few weeks to do, was to bring the telescope down to its operating temperature and to check the focus of all the 18 mirrors individually. And that took a while because there's a lot of mirrors and there's fine motions of a 1 micron, say, is a detectable difference in the quality of the image. And that focusing procedure to make a common focal plane took several weeks. Then the instruments, the 4 instruments on the James Webb, each had to do their own focusing procedure. And the images that were released recently showed that at this point all the instruments on James Webb have been able to form sharp, diffraction-limited images. So the entire telescope structure, the mirrors, the focal plane that they come to in the different instruments are all working in concert to produce sharp images. Now there's more calibration required because each instrument has many different instrument modes of taking data, fields of view, filters, different modes of doing imaging or spectroscopy, and each of these modes has to be tested and calibrated. So that's going to take another few weeks. So that's why people are thinking that it's really not going to be until June that the early scientific observations will start to come in.
The next question is from Lamont Lathan, who's on with us live, and asks, what role does methodical naturalism play in astronomy? Why aren't supernatural hypotheses accepted as having any explanatory power?
I think it comes down to the meaning of the word. Scientists look for natural explanations for physical phenomena, which is to say explanations that follow the logic of the scientific method, where effects have causes that we can identify, where causality operates, and where we can identify a mechanism for any behavior or observation we make. Now, not always are we successful in that. Science is imperfect and it's a continuing quest. But the naturalistic way of doing science based on natural phenomena, physical phenomena, has been very successful over time. So the really simple answer is that there's no need yet to reach for a supernatural explanation for anything that I've seen, certainly in the realm of astronomy or physics. It's not that it's ruled out that there might be extraordinary phenomena that require extraordinary explanations. It's just that nothing that's been published or corroborated or observed so far requires that. So it's a very good strategy based on the history of science so far to look for naturalistic, physically based mechanisms to explain what you see.
The next question is from Dion Mack. Is our solar system in a state of equilibrium, or does it only appear to be stable looking at its arrangement in modern day times? Surely if we lived during a major extinction event, it would be hard to suggest that our solar system was orderly.
So our solar system is long-term stable, which is to say that over time frames of millions or tens of millions of years, the orbits of the planets do not noticeably alter. Now, there are minor changes that can occur within those time frames. The obliquity, the tilt of a planet's orbit, its eccentricity can change, but the planets are long-term stable in the sense that they are not going to migrate towards the sun or be ejected from the system. That would be a dramatically unstable situation. And things like extinctions don't really play a part in this, because when an extinction is caused by a major impact, a comet or a meteor on the Earth or an asteroid, that is also not enough to alter the orbit of a planet. So while it's a dramatic, catastrophic impact on a biosphere or on the climate of a planet, it doesn't alter its astronomical situation. On longer timescales, however, of hundreds of millions or billions of years, computer simulations of our solar system's configuration suggest that it is not long-term stable, that over sufficiently long timescales, small orbital irregularities gradually build up, they can reinforce each other, and then occasionally you get a resonance situation where you have nonlinear enhancement of an irregularity, and that boosts it enormously. And those irregularities can lead in the long term, very long term, to the ejection of planets from the system or dramatic changes in their orbital positions.
The next question is from Cesar, who sent an email. The Heisenberg principle sets a theoretical limitation to the observation of small things like atoms. Does this principle, or is there a similar principle that also limits observations somehow in astronomy?
Astronomy is not usually working in a regime where the Heisenberg uncertainty principle operates. It does, of course, however, operate at the level of the individual transitions, that is, atomic and nuclear transitions that astronomers observe even out there in the universe. So, yes, the quantum uncertainty principle does apply in terms of the energy transitions that astronomers look at in atoms and molecules that compose astronomical objects. But the astronomical objects themselves are consisting of such large numbers of atoms and molecules that these uncertainty effects are invisible or negligible.
The next question is from Hernan Reyes, who sent an email but is on with us live. You've discussed the internal tidal heating and possible cryovolcanism on Europa. The question is, Europa's surface has these big slabs of ice, which are numerous and very big, these ice rafts. And the question is, the sources say that such cracking, shifting, and settling takes place over tens or hundreds of thousands of years. So why would it take so long to crack the ice and move it around, especially if there are these geysers that erupt and push things around? What's the process that takes so long for moving these ice rafts?
I think the idea, first of all, there's some uncertainty over these timescales for motions. We don't observe them directly, of course, even though we've got data now for a few decades. So we're dealing with models of the European cross-section, essentially. And remember, we just don't have any very recent data. The Europa Clipper, we are sending missions out to Europa, but that's a ways off. The only data we have so far from up close, apart from telescopic observations, comes from decades ago. And so we have densitometer and magnetometer measurements, and that's the basis of belief that there's a liquid ocean under the European crust. But the models for how deep the ocean is, how thick the icy crust is, and what its internal structure are very uncertain. Essentially, they're degenerate. You can make multiple plausible models that explain the limited data we have, and thereby lies the uncertainty. But the speculation is that the icy crust is actually very thick, perhaps 5, perhaps 10 kilometers deep. And in that situation, also very frigid, and ice at that enormously low pressure and low temperature is extremely brittle, but also extremely hard, harder than granite. And so you've got an extremely thick icy crust, you've got very tepid heating from an internal ocean, and you've got rigid material, essentially. And so even though cracks and fissures can develop and there can be geysers, the underlying situation is one of rigidity, of enormous mass and rigid ice. And so that's why the timescale is correspondingly long.
The next question is from Mark Essex, who's on with us live. What is the difference between astronomy and astrology? Were they once the same thing? And if so, what happened to separate them?
Yes, they have a long and interesting history together. So astronomy and astrology, if not the same thing, were certainly closely related, very closely related. And it's well known that some of the famous Renaissance astronomers, like Johannes Kepler, for example, cast horoscopes, and so they acted as astrologers and astronomers. So astrology is the idea that the celestial objects, especially the planets, the sun and the moon, have an effect on human affairs, and on personality perhaps, and on how things behave and on our outcomes as human beings. There's no scientific basis for that. But in an early age, a pre-scientific age, it's natural to think that astronomical objects might have an effect on humans. The sun obviously does, and at some level the moon does. And so it was extended to the planets as these special objects in the sky, the wanderers, for the Greek word for planet is wanderer. So astrology had a natural sort of folk tethering in populations in a pre-scientific age. And astronomy, of course, developed slowly over time. It took a couple hundred years to truly understand the nature of the planets. And it took a theory of gravity from Isaac Newton. So the separation of astrology and astronomy did not happen overnight, and it took a while after the Renaissance until Newton's theory and then beyond. So they are now separate, and in the modern world, no astronomer gives astrology credence as a scientific theory. The words are often confused by the general public because the number of letters different is very small, but they really are not the same thing at all.
The 800 millimeter telescope project, who's on with us live, asks, do we have planet rotation times all sorted out and explained for our solar system? Do we know why the Earth has 24-hour days and why Venus has 200 plus and Jupiter 8 hours?
We don't know the specifics of that in a sense of being able to predict them. At some level, the orbital periods of the planets, the spin periods of the planets, are a reflection of initial conditions. They reflect the angular momentum of the material that formed that planet at the time that planet formed in the solar nebula. So initial conditions sort of lock in some part of that rotation. It's basically a reflection of the angular momentum of the swirling cloud that accreted to form a planet at a particular distance from the sun. That, of course, can be modified by other conditions. In the case of the Earth-Moon interaction has an effect. And in fact, the Earth-Moon interaction is causing the day to get very slightly longer every year. It's a measurable phenomenon. And so if a planet has a large moon or a lot of small moons equally, it can alter that angular momentum. There's transfer of angular momentum and energy, which affects the spin time. So there are things, and then if there are close encounters between planets in the history of the solar system or impacts that are substantial, that can also affect their spin rate. So it's initial conditions plus a series of circumstances that happen downstream. And that means it's hard to look at the spin period of each of the planets and say, I understand exactly why it's that number. We only understand it in a very general sense.
John M. sent an email. You mentioned in the last session that there will be a transmission this year directed to TRAPPIST-1 in an attempt to contact potential intelligent life in this exoplanet system. Because the distance between our solar system and TRAPPIST-1 is 39 light years, it will take that message 39 years to arrive. We've had radio and television broadcasts on Earth for much longer than that, so one would expect that these signals have reached TRAPPIST-1 decades ago. So what's the difference between the random radio broadcasts and the transmission of METI?
Sure, that's a sensible and logical question. We have had radio and TV for quite a while, close to 100 years. And those signals have been leaking away from the Earth and traveling in a sphere, essentially, out from the Earth for quite a long time. I actually did the math of this because it became such a sort of trope, if you like, that these signals are out there, and so aliens have seen our early TV shows from the 1950s, and they're either horrified and think we really aren't worth contacting because we're not that smart, or they're intrigued and want to see what happens in the next season of I Love Lucy or Gilligan's Island, and that's being flipped. But still, when I did the math, I actually got interviewed on NPR about this some years ago, and the answer is a little disappointing. If you work out the dilution of a spherically traveling radio signal, even given 100 megawatt transmitters that we've been using since the 50s and 60s, then that radio signal lowers so rapidly with the inverse square law that it goes below the level of the microwave background hum of the Big Bang itself before it even leaves the solar system. So this whole idea that the wave of our radio and TV transmissions is sweeping over hundreds of Earth-like planets is simply wrong. That signal does exist. It doesn't go to zero, but it's essentially down at the level of cosmic noise before it gets very far beyond the solar system. The METI experiments, the Gilhooly experiment to TRAPPIST, and the potential experiment with the fast Chinese telescope next year or the year after, these are targeted experiments where we're going to beam radiation. So it has much higher energy when it's being specifically beamed by a telescope to a target than if we just use random leakage of our casual radio and TV communications.
The next question is from Lawrence K., who's on with us live. Does Einstein's cosmological constant, or his greatest blunder, basically describe dark energy as we understand dark energy today?
Yes, it's pretty close to that. Einstein's cosmological constant, or his greatest blunder, is a countervailing. If you've solved the equations of general relativity, then the natural result of those equations is either expansion or contraction. It's a dynamic solution in general relativity if you solve it for a universe. We believe the solution is an expanding solution, and then we connect it to the idea of the Big Bang. When Einstein developed his theory in 1916, and he went to Mount Wilson Observatory soon afterwards and asked the astronomers the state of the universe, at the time, of course, they said the universe was static because all they knew of was one very large galaxy, the Milky Way. External galaxies were not yet discovered. The expansion of the universe, the Hubble expansion, was not yet discovered. And so Einstein realized his equations were predicting the wrong thing. They were predicting a dynamic universe. And so to counter that natural expansion in the solutions, he introduced a term with the opposite sign that would go against the expansion. So it was opposite to gravity. And that is the cosmological constant. And that is, of course, also why it happens to fit quite well the idea of dark energy, which is also working in opposition to gravity to cause the universe to accelerate faster and faster. In Einstein's framing of the cosmological constant, it was a constant of integration of the general relativity equations, and so it did not vary with time or in direction or in space. And so far, our measurements of dark energy are consistent with that too. So in simplistic terms, yes, the dark energy matches conceptually and mathematically with Einstein's cosmological constant, but that is not a very strong statement because we know so little about dark energy at this point.
All right, the next question is from Astro, who's on with us live. What do you think about the announcement that the Event Horizon Telescope will give tomorrow? Do you have any insights or speculations?
Yeah, I'm not sure what it's going to be. They've been observing several targets. They've obviously been, their splashy discovery of M87 was spectacular. That's now a couple of years ago. It's known that they're looking at the galactic center, so it's a good guess that the galactic center is going to be part of this announcement, but they've also been looking at several other supermassive black holes. The Event Horizon Telescope is fairly challenged to do these black hole imaging experiments because it requires a black hole to be some combination of either very massive or very nearby. And so the galactic center black hole is not that massive, a few million solar masses, but it's only a few tens of thousands of light years away, whereas the M87 black hole is billions of solar masses, but it's millions of light years away. So it's a trade-off between those two things. And that means the number of objects or black holes that the Event Horizon Telescope can do its imaging for is really quite limited until there are some major upgrades to the technology of that interferometer.
Jake Johnson, who's on with us live, would like to know if you can explain what tidal forces are.
A tidal force is a differential gravity force. So gravity declines in Newtonian gravity. The force of gravity declines as the inverse square of the distance. And so, you know, the gravity falls with distance in a particular mathematical way. When objects have a physical size and a significant size, then, and the two objects are close to each other, then you can see that the gravity, and a gravity of a spherical object like the Earth, operates as if the entire mass was concentrated at the center. But that's a simplification. When the object is extended like a planet, like the Earth or the Moon, then clearly the Moon is going to exert stronger gravity on the near side of the Earth than on the far side of the Earth because the distance is larger, and vice versa. And that difference in the gravity is a stretching force, and that's the tidal force. And in the case of the Moon and the Earth, that's what causes the tides.
George Papadopoulos is on with us live. Professor, what is the earliest example of true astronomy in human civilization? I've heard about markings that may have been a kind of lunar calendar. What can we point to that was clearly astronomy?
It's a controversial thing to go back into prehistory and talk about astronomy, but people still do it. So, the earliest unequivocal forms of astronomy probably date back to the ancient Greeks, the philosophers and people speculating about physics and astronomy who were using logic and the scientific method and simple observations with the naked eye. That's clearly astronomy. Once you go back to the previous civilizations, there's positional astronomy, so we definitely have evidence that the Egyptians and Chinese and the Babylonian civilizations were doing calendar observations, and that's astronomical observation, sort of back to about 5,000 or 6,000 years ago. Before that, it gets much harder, because then you're talking about hunter-gatherers or nomads or people who had left no written record or had no written language. And I would say probably the best evidence of astronomical observation or implication goes back 30 or 40,000 years, because there are bones and calendar sticks that have been found in Africa and other parts of the world where the number of markings indicates they were keeping a lunar calendar. In other words, there were tick marks or scratches or notches in a bone or on a wall, sometimes painted onto a wall, which indicate a lunar calendar in operation. So if you want to go back that far to primitive people, nomads in the early Earth, then there's some evidence of astronomy in play.
The next question is from Prabir, who asks, would you please elaborate on the concept of quantum entanglement, and what's the evidence that we have for this phenomenon or how it works?
Quantum entanglement is a real phenomenon of quantum physics that's been now observed in the lab routinely, and it can be created routinely. It's a repeatable phenomenon for several decades now. So normally a single particle is described by a quantum mechanics description, and it has a series of states, quantum states, and has a probabilistic definition of its energy, its momentum, and its position. When you start to have more than one particle in a small space, by suitable methods, often involving a vacuum and extreme cooling, you can create coherence in the quantum states between two particles, which means the two quantum states are linked somewhat or correlated. And that correlation or linkage is essentially entanglement. That's what entanglement is. And that means that the state of one particle is dependent or depends on or is correlated with the state of the other particle. And if you interrogate one particle, say in an entangled pair, you affect the state of the other particle, and the information you can extract from that particle depends on its partner. So this is coherent information between individual quantum systems. And this coherence has now been observed over substantial distances, meters in the lab, and in slightly more controversial examples, maybe hundreds of kilometers. So it's a pretty robust mechanism. It's the basis of quantum computing, of course, which is essentially using the entanglement idea to make a parallel computer, parallel processing of a computer, which, as we know in conventional computers, leads to enormous speed and efficiency.
TJ, who's on with us live, would like to know, is the University of Arizona making more borosilicate mirrors?
Yes, the University of Arizona has almost always got a mirror in play or nearly in play. Actually, just this week we had the high fire event. High fire is the colloquial term for when the spinning oven reaches about 1170 degrees C and the borosilicate glass melts and is spun into a parabolic shape. We had a high fire event for a 6.5 meter mirror that's destined for a telescope in South America. And we make mirrors by contract with other partners. These are not always facilities the University of Arizona is a formal partner in and will get telescope time with. The bulk of the mirror making, though, has been the 8.4 meter mirrors that will be part of the giant Magellan telescope to be built in Chile. And we're up to our 5th mirror on that. So yeah, the mirror lab is pretty always working, and they can make about 1 mirror per year and then polish the mirror, which takes about the same amount of time.
Wendy sent an email. Martin Rees recently wrote that he believes Mars will only be colonized by an intrepid few, and they might evolve cybernetically to alter human evolution. How do you see Mars colonization progressing?
I think Martin Rees is correct on that. The cost and expense, difficulty and danger of Mars colonization is often underestimated, and in particular maybe by people like Elon Musk, who really have that as their ambition. And they know what the technical challenges are, but they're firing people up about it, so they don't want to overplay the risks, the dangers, and the expenses. But for all of those risks, dangers, and expenses, it's very unlikely that more than a handful of people will be part of an early Mars colony. Certainly not enough for it to be a self-contained, self-sustaining system. So in other words, the first Mars colonies will be resupplied from the Earth periodically, episodically. It's not that people will go there, spend their lives there, and die there initially. He's right, however, also in the fact that the people who are going to self-select to be part of these very brave, adventuring souls will tend to have very technology-forward attitudes. And there is great advantage if you're in an alien and hostile environment like Mars, very artificial environment, to being willing to alter your own genetic makeup, to do hacking of your own gene, as it's called, to improve your adaptation to that difficult environment. So the technology-forward nature of the first Mars colonists mean that it is quite likely they will do some quite radical genetic modification of themselves. And I would certainly expect that to happen.
Michelle Vasquez asks, if the further we look into space, the further back in time we are looking, are the stars we see actually much further from us than we observe, or the galaxies for that matter?
Well, that's an interesting question. In the case of stars, no, because we really can only see stars in the Milky Way galaxy. And the stars we see in the Milky Way galaxy, even if we're looking back in time, are part of a bound gravitational system. So if we could see a star on the far side of the disk of our galaxy, it might be 40 or 50,000 light years away. So we're seeing it as it was 40 or 50,000 years ago. But that star is in a multi-hundred million year orbit of the galaxy, and so it's not going to change its distance over that time. But when we're talking about galaxies, then the situation is quite different. So distant galaxies we see as they were 5, 10, maybe even 12 billion years ago. And that means the light we see now was emitted when the universe was much younger than it is now, much smaller, much denser, much hotter. And so if you ask, what are those galaxies doing now, because we had to wait so many billion years for their light to reach us, then yes, those galaxies are now going to move very far away. And in an accelerating universe, some of those galaxies now may be moving beyond our vision. So the only reason we can even see them at all is because we're looking back in time to when the universe was smaller, denser, and hotter, and the light could reach us.
The next question is from Supreme Scientist. How many planets do you think were originally in our solar system?
Well, we don't completely know. This archaeology of our solar system is not an exact science. We know the formation process. We know the age quite well, 4.54 billion years with some precision on that second digit. And we know that there were interactions among the giant planets that moved their orbits early on. And those interactions early on are what opened the door for the possibility that there were more than the 8 major planets, the accepted planets in the solar system early on, and that early interactions, instabilities, and chaotic orbits could have led to the ejection of one or more planets. So that's certainly a possibility, just because of the way the orbital mechanics work and the chaos of the early solar system. You can lose planets, you can also capture planets, and that's of course what we think happened with Pluto, which is a dwarf planet, but everything about its orbit suggests that it was captured from somewhere out in the Kuiper belt. And if you follow a solar system over time, there may be other instances of capture too.
The next question is from David Wismer, who asks, do two sections of space-time that are moving away from each other faster than the speed of light know that the other have expanded? And if so, how?
No, if you're dealing with places in space-time that are moving away from each other at faster than the speed of light, then they are not in causal contact. In other words, they cannot exchange signals with each other or know of their existence. And that is the situation of our universe, because the early history of the Big Bang involved a significant period of time, several billion years, when all parts of space-time were moving away from each other faster than light, and so we're not in causal contact. So that's a pretty standard part, actually, of the Big Bang model, that situation applies. And of course, as a sidebar, that's one of the reasons that the inflationary idea was come up with, because the smoothness of the universe, the uniformity of the microwave background, the general uniformity of the universe across space and time is not easily explicable when different parts of the universe were not in causal connection with each other. How did it homogenize? How did it smooth out its temperature if these regions couldn't communicate? Inflation provides an answer for that.
Petra, who's on with us live, asks, is there potential in finding a new particle or new physics in the muon G2 experiment, and what are some of the possibilities of those outcomes?
Yeah, the muon G2 experiment is the recent experiment which has implicated new physics beyond the standard model of particle physics. It's a pretty subtle effect. I think it's a fraction of a percent in the moment of the muon. A muon is a fundamental particle that is about 270 times the mass of the electron, and it's part of the standard model of particle physics, but this property of it has been deviating from the standard model significantly. And the truth is, the observations themselves are still a little controversial because they're quite subtle, although two different groups have seen roughly the same thing. The interpretation is definitely up for grabs, because I've seen several dozen papers just in the last few months with quite different speculations as to what's going on. So standard model of particle physics appears to be slightly violated in this experiment, but the explanation of why and how and what it means is still very unclear.
The next question is from Aman, who asks, can negative mass create a white hole?
Well, there's no formal way to talk about negative mass in conventional astronomy and gravity theory. So you can mathematically make a conception of negative mass, but the question is, does it exist in the real universe? Is it a real physical phenomena? And at the moment, we don't think that it is necessarily, and therefore any imputation of white holes from negative mass is also beyond the realm of conventional physics.
The next question is from Crawley, who is on with us live. Do all of the elements in our solar system originate from our sun?
In terms of chemical elements, no, because the solar system contains objects that all formed roughly at the same time, 4.5 billion years ago. And so all the elements, the heavy elements, the stuff that the Earth is made of, oxygen, nitrogen, iron, nickel, etc., and the things that humans are made of, carbon as well, those elements pre-existed the solar system because they all formed, everything collapsed or condensed or formed out of the initial solar nebula. And that solar nebula was material that pre-existed. And so if we're going to explain the chemical elements, we have to look before that and beyond that. And the natural explanation in stellar evolution is that those elements were created in previous generations of stars. Some fraction of those elements might be trapped in the center of the star as it died as a white dwarf, black hole, or neutron star, but some fraction of those elements are ejected in supernova events or nova events, or just the general loss of gas that most stars experience in their lifetime. So that's where those elements came from. They came from other previous generations of stars, possibly quite far away and possibly billions of years before the formation of the solar system.
So in a related question, Rajarshi asks, or says, I learned that the heavy elements were forged in the core of dying stars under tremendous pressure, but how are even more dense or heavier natural elements formed, like lead, uranium, or gold?
Well, there are now seem to be two substantial mechanisms for these. One is the supernova blast wave. So rather than being formed in the dense core of a collapsing star, they're actually formed in the blast wave that results after that core collapses. So the core collapse of a massive star is followed by a bounce as the matter meets an immovable object. Essentially, it becomes so dense that the momentum reverses. And that blast wave traveling out through the envelope of the star instantaneously shock heats to temperatures of several billion degrees. And that temperature is enough for explosive nucleosynthesis to take place. And so that way you can form all the heavy elements beyond iron, up to the transuranic elements even, the radioactive elements, so certainly including gold, silver, platinum, and so on. So that's one mechanism, and that's been well known for half a century. More recently, we've learned that neutron star collisions, which are definitely going to happen as neutron stars orbit and collide, can also put incredible energy into the system and create explosive nucleosynthesis of those same heavy elements. And that channel for heavy element creation, neutron star collisions, is now thought to be almost as important as supernovae.
Harry Bell, who's on with us live, asks, how integral do you think philosophical and ethical questions should be in the pursuit of science? For instance, in a project such as METI, where success, however unlikely, has enormous impact.
That's a good question. In general, science, of course, does depend a lot on philosophy. I mean, physics is natural philosophy until, I think, the 1970s or so. If you did a degree at Cambridge University in England and you were doing a physics degree, it was called natural philosophy. So physics and philosophy and astronomy and philosophy are very closely related fields, and so there's a philosophical underpinning to how science works and to how we explore and understand the universe. Ethical issues also come in. Generally, astronomy doesn't have situations with much ethical implication. Worrying about how the universe formed or how stars die doesn't really have an ethical implication. But the example of METI is a case where astronomy does have an ethical context. And the situation there is that some people vehemently disagree with the idea that we should actively message potential intelligent alien civilizations because they think it would be hazardous to do so. If we don't know the intention or inclination of those civilizations, we might be exposing ourselves to discovery, annihilation, and so on. That's the specter of doing METI if you don't really know what's going on. So that's a clear ethical issue. The exploration of exploitation of space resources is another place where astronomy touches on ethical issues. And so there are some areas like that. Another one I would mention that's big in astronomy now and has become more recognized over time is that astronomers often put their telescopes in places where indigenous people have historically declared them to be sacred spaces on the tops of mountains. Mauna Kea is the most prominent example, but there are others. And so astronomers have to bear in mind that what they're doing, while it may not seem like it's altering the Earth or anti-environmental, could be dealing with some cultural issues that require real sensitivity and awareness of ethical issues.
The next question is from Jeffin Raja, who asks, how did they determine the speed of light in ancient times? I mean, I don't know that it was that ancient, but how did they determine the speed of light in the earliest experiments, and what techniques are used today? What types of equipment do they use?
So it took a long time to measure the speed of light. We really needed the advent of the modern scientific method because 300,000 kilometers per second is so fast that light travels essentially instantly over terrestrial distances. Galileo did an experiment in his youth where he had a companion stand on a mountaintop, and at the range of it, they each had a lantern with a shutter, and Galileo arranged that he would open his shutter, and when his friend saw the light, he would open his shutter, and when Galileo saw the light back, they'd try and time that reverse, that double distance across between two mountaintops. And it was probably only a distance of 5 or 7 miles. And of course, light does that in a tiny fraction of a second, and Galileo was only using his pulse as a timing device. So that failed. It was essentially instant. So that's the nature and the problem of experiments before proper scientific method. The first plausible and not bad measurement of the speed of light was an astronomical measurement by Romer, Danish astronomer. And he used a very clever method where he used eclipses of the Jovian moons. So the Jovian moons travel behind and then in front of Jupiter as seen from the Earth. And he used a timing method which used the difference between the moon being in front of Jupiter and being behind Jupiter, the distance, the time that that extra distance took. And that is a measurable amount of time. So the Jupiter-Moon timing experiment of Romer nailed the speed of light to about 10% accuracy. To do much better did not happen until 20th century. And now, to fast forward to the present day, microelectronics and superfast electronics can essentially operate at picosecond time resolutions. And in a picosecond, light doesn't travel very far at all. So we've got an extremely precise measure of the speed of light now.
Isla would like to know, do you have to send a probe to find out if a body in space has a magnetic field?
Usually you do, because you need to actually measure it. Magnetic fields don't make themselves obvious. The exception, however, is for stars, because stars, if you can see the star with sufficient resolution, stars have sunspots, they have flares, they have chromospheric activity, and so even if you can't resolve the star, like making a map of it, you can look at its activity over time, or perhaps its X-ray emission, because the X-rays come from a secondary phenomenon associated with magnetic fields. So you can infer the presence of magnetic fields in stars fairly well from astronomical observation. For planets, especially for planets beyond the solar system, the exoplanets, it's not possible to determine if they have magnetic fields. We can assume that some of them do. The more massive ones should have liquid metal cores and would retrain a magnetic field and create one by a dynamo mechanism. But in that case, we simply don't know yet.
The next question is from Remus, who's on with us live. How far can the JWST see? Can it see? Well, I'll just leave it there and you can fill it in.
The best guess is, since James Webb Space Telescope was designed to measure first light in the universe, that's the generation of the very first stars and galaxies. We don't actually know which came first. That's one of the questions that James Webb is supposed to answer. We're going to guess that that happened between 50 is the smallest and maybe 100 or 200 million years after the Big Bang. Remember, that was 13.8 billion years ago, so it's a very small fraction of the age of the universe. And James Webb is designed to be good enough to see that far back. And so that's how far back James Webb hopes to see.
Excellent. It's 11:01, so we have time for like one more question. We did start a couple of minutes after the hour. Is there a possibility of a mission to the planet Uranus to study it or its satellites?
Yes, there is. And actually, a few weeks ago, the planetary scientists had their version of the astronomer's decadal survey. So Planetary Science and Astrobiology Decadal Survey was released by the National Academy of Sciences several weeks ago, last month. And in that report, it prioritized its flagship missions for the next decade and beyond, actually, because some of these missions take 10 years just to plan and launch, and then another 10 years to get to their target. So unlike the astronomers, the planetary scientists actually have to think in more than a decade timescale. And one of the flagship missions, for probably not the next cycle with NASA, but the cycle after, is a Uranus flagship mission. To go there, to explore the planet up close, to look at its moons up close, and to do the kind of work that Cassini did, for example, on the Saturn system. That's a very exciting mission, but realistically, it's very expensive. Probably the price tag, I think, was $7 or $8 billion. And the timescale for actually getting there is the early to mid 2040s. Thanks. That was a good question at the end about planetary future missions, and a lot of ground covered today as usual. So appreciate your questions as always. We'll be back with you. Our next couple of live sessions, I think Matthew can tell us when they are going to be or what they're being advertised, and thanks for his help in facilitating.
Yes, so the next two live sessions are in 2 weeks on Twitch, so that'll be May 25th. And then we probably will only have one in June because of various travel schedules. And so the one in June will be on the 22nd of June. And so just things get busy for us sometimes during the summer. But we're looking forward to seeing you all in 2 weeks, and have a great rest of your week and weekend. Take care, everyone.